Okay, let me start. So welcome all to the AI for Good meetup talk. This is the talk for the month of January. So today I have the pleasure of having Dr. Annika Reinke from Germany. She's currently the deputy head and group lead for validation and intelligence systems at the German Cancer Research Center. Dr. Annika Reinke earned her PhD degree in 2023, so last year. She has been focused on AI-based biomedical image analysis. You can read, she has a Google page with all her scientific publications. She has written many interesting articles. So in her dissertation, she wanted to systematically reveal critical quality issues in validation practices and to propose solutions to eliminate them. So she has written papers on, for instance, on imaging competition and so on, like very interesting papers. So today she'll talk about the talk there will be validation matters. So ensuring that we have a trustworthy AI in healthcare. Okay, so the floor is yours.
Thank you so much for the kind introduction. I will share my screen. Second, and it's loading. Okay, here we go. All right, so yeah, as already said in the introduction, my thesis and my work is all about validation, a topic that is sometimes perceived as not so important, not so interesting, but very relevant when we talk about AI and something that we need to ensure that our algorithms are trustworthy. So there was a recent study in 2022 where about a representative amount of people in the UK were asked about how they perceive AI, what they think are important applications, and so on. And as you see here, more than half of the people that were asked said that using AI to predict the risk of cancer is extremely important, but they're still concerned that we rely too much on this technology compared to trusting human doctors. On the other hand, if we look at the different topics, they rated assessing risk of cancer as the most beneficial goal of AI. So we have somehow this discrepancy between us having something that is really important and something that people don't really trust. And I think the validation is an important part behind all of this topic and why we're not trusting our algorithm. Because from the AI developer perspective, we often think of ourselves as developing these awesome new techniques, working on new model architectures, on new tricks to make our models even better. But we often forget that there's much more behind AI than just models. It's also about dataset design, about high quality annotations, about metrics, rankings, and so on and so forth. So there's a lot more things that we need to consider. And I would like to start this with an example of why I think validation is important. So perhaps you know this Ariane 5 disaster. So back in 1996, there was the very first flight of a new rocket, the Ariane 5. And as you see here from this video, it started and then suddenly, directly after the start, flipped into the wrong direction and exploded. So what happened here? Perhaps you know the story and then you already know it. But generally, the problem was they were working on this new rocket. So they're mostly working on the hardware, but not the software. So they used the old software from the older rocket together with the new hardware. And this new relationship was just not tested. So the problem was, to be short, they used a 64-bit floating point value that should have then been stored in the 16-bit integer variable. And as you may imagine, this just didn't work. This caused then a negative value. The rocket flipped in the wrong direction and self-destroyed. So this is just one example, of course, a very dramatic one. What could go wrong if we're not validating our algorithms correctly? And in healthcare, I would say these consequences could also be very dramatic. So back in the days where COVID started, there were many researchers working on using AI to help predicting or diagnosing COVID from X-ray or CT scan, so something that you see on the right here. And there was this one publication which I found really interesting, because they had a look at all of these different methods that evolved during that time and had a look at also which data sets they used. So commonly, if you validate such a thing, you typically use a control group, so people that are healthy, and a group of COVID-19 patients. However, very often in that study, it was seen that the data set for the healthy patients were only from children, whereas the COVID-19 patients were only adults. So the algorithm didn't learn whether someone had COVID or not. They learned whether someone was an adult or children. So completely wrong direction of what we actually want from our algorithms. And I think validation would have helped here a lot. And I think that this tweet here is a good, actually very, very true, because this person said that the challenges that we have with AI are very similar to those that we have when we build an organization culture. So for example, lack of diversity is always a problem, not preparing for edge cases, biases, or tracking the wrong metrics. And I will talk about a few of these in the next few minutes. So I personally see validation as an enabler for trustworthiness. If we validate correctly, we can also make sure that we're going in the right direction, that our algorithms are doing the right thing. Also, if we don't actually know what the algorithms are doing, we could still control a little bit better if we validate correctly. So when we talk about healthcare, I don't know if you're familiar with all of these papers, but there are many, many deep learning algorithms nowadays that basically claim we're even better than the doctors. We're outperforming the doctor's performance. The AI is so good in solving tasks. However, when we look at all of those, and every individual paper will basically say we're outperforming all the other methods. And how do we then know which method is best? This is one question that I'm interested in and that we're also doing some research on. And generally, in staying in healthcare, if you have a new medication or a new treatment, you typically perform a clinical trial to assess whether the new medication is better than the old one. And we have an equivalent for AI, which are competitions. So in these competitions, algorithms compete against each other under the very same conditions so that we can really compare them. It's not their own paper where they're stating we are outperforming all the others, and they're using their own data sets, their own hardware, their own GPUs, and so on. Now, here in a challenge, in a competition, all of that is fixed and we have fair conditions. So they're competing against each other. Perhaps you know that from Kaggle, for example. And the winner of such a challenge is typically somehow famous, because on the one hand, you often have high prize money, which is of course a nice incentive to participate in such a challenge. On the other hand, you're the new state-of-the-art method for a particular problem. So you somehow get a high level of citations, which from researcher perspective is extremely important. And also the algorithms that win a challenge have a higher chance of being translated into clinical practice. And if we look at some numbers here, we see that the impact of challenges is steadily increasing. So the number of challenges is rising every year. And also we have challenges for every purpose, every problem that you may imagine. For example, we may have a challenge for polyp detection, or for cell tracking and segmentation, or for whatever else you see here, for brain images, for MRI, for CT. So you will find a challenge that is suited for your research purpose. So these challenges have become very important for research on the one hand. They're also often providing new data sets that can then be used for validation. And this is a critical point, because in healthcare, we often lack data sets because, due to privacy issues for the patient, of course. So challenges are very important. You will find a challenge for every application, for every modality that you can imagine. And why is it such an important topic? Well, if you think of the way that research articles are recently presented, you will see that in most of the papers, you see these comparisons. So a table where you're comparing your method against baselines, against other state-of-the-art methods, and in which you're performing a mini competition to make sure that your algorithm is better than the others. So everything that I'm going to talk about also is relevant for general algorithm benchmarking and for every individual paper that we see. So as I told you, challenges are currently the state of the art for comparative benchmarking. They are really important and have a high impact on the research community. And also, many publications and many individual researchers copy whatever a challenge is doing. So for example, they use the same data, the same metrics, the same rankings to compare themselves against the challenge participants to show that they are even better than the winner of a challenge. Now let's assume that a challenge is organized in a thorough and very well organized fashion. Then we can see challenges as a framework for trustworthy AI because the whole research community will just follow them. This is of course a nice thing. And because challenges are such important, we had a closer look into what's happening with them and their quality. And we're concerned about the question, is the winner of a challenge really the best? Because that's, of course, where all of our hypotheses are based on, that winning a challenge, the winner of a challenge is really the best for a specific problem. So we had a look at different components that are related to validation. And the first one that we looked at is reporting. Okay, reporting, again, may sound a bit boring at first, but it's an important and essential part of how we present results. And as these people here from this publication state, the one practice that can universally be commended is transparent and complete reporting of all facets of a study. And this is important for us to be able to reproduce results, to be able to interpret results, and trust the results that are reported, not only for a challenge, but also for every research that we can imagine. So we had a thought of what are parameters that are important to report. So there are a couple of things that are kind of obvious. So for example, how large is my data set? Which metrics did I use? But there are also some that are not so obvious at first. So for example, are the participants allowed to use their own data? Or who annotated the data? How many people annotated the data? How do you treat missing values? And so on and so forth. So we created a list of all of these parameters, and we had a look at more than 500 competitions. And unfortunately, the reporting practice was quite poor. So a median of 64% were reported, which is not that much. And only 6% of parameters were reported by all challenges. And with these parameters, I mean quite obvious things like the title of a challenge or the website. To give you some examples of why this is critical, 85% of challenges didn't give instructions on whether the participants could have used their own data in addition to the training data provided by organizers. And if we think of the purpose of a challenge being a fair comparison across algorithms, imagine you have a team that just has access to their own data set, like thousands more images. And then you have a team that just don't have access to that data. That's definitely not fair. And in 66% of all tasks, there was no description on how the reference, so the gold standard annotation, was performed. And that's again critical because our algorithms cannot really be better than the reference they're learning on. So we need to know how it was generated and if we can trust the quality of these annotations. So putting this all together, we thought, okay, this is really critical. We have to do something against it. And we then created a reporting guideline that really guides researchers and practitioners to report their challenge. So you basically have really a list of parameters, and you can just go through that step by step and make sure that you report that in your publication or on your website. And speaking of the experience from a challenge organizer, I also organized a challenge and I followed that guideline that really makes it easy for you. So it's really, you can just stupidly just follow all of these things, which is a nice thing. And it just also introduces another level of standardization. We also registered these with the Equator network, and this is a general umbrella organization for enhancing quality and transparency of health research. Here you also find very common guidelines like the consort statement for clinical trial, which I think is one of the most well-known statements. So this is nice that we now have this reporting guideline. So we made sure that we improved the quality control of challenges. So first, typically challenges in our field are organized at a conference. So we introduced a peer review process for these challenges where we had direct control. So reviewers going through the challenge design based on this guideline, giving comments on which things to improve. And only if a challenge was had a high enough quality, we accepted that challenge at a conference. However, after that, we didn't have quality control, because after a challenge was accepted, we couldn't control every single challenge, like, I don't know, 50 to 100 challenges a year, to ensure that they're really doing only what we accepted. So we introduced another step here, which we call challenge registration. And perhaps if you're a little bit familiar with how clinical trials work, you know that if you're conducting such a trial, you have to upload your full study design online before you do anything, before you get the data, before you do any analysis. And we wanted to do the same thing here for these challenges. So after the challenge was accepted, we uploaded the full design document online, where we got somehow an indirect quality control. We somehow peer pressured people to stick with what they actually told people, because otherwise participants would just look at these design documents and see, well, you reported that differently. So we somehow made sure that they followed these what they accepted. And they're easily accessible. You just have a list of challenges that were accepted, a DOI. And if there is a change to the design, challenge organizers had to report that back to us. We did another review process, and we had a versioning control where you could directly track all the changes to the design. So this was a really nice step forward, and we do this for, I think, 4 years now, which works really well. So we definitely improved the reporting practice here. It's not perfect, but still it's a step forward. But after we looked at this, we went to the next problematic thing, which were rankings. And as you may imagine, a challenge is a competition. And in a competition, you want to know who is best. So we create a ranking to determine that. But it's not so straightforward to calculate these rankings. For example, let's say we have a bunch of different algorithms. We have a bunch of different images. And for each of these images, for each algorithm, we get a metric score. So what do you do with these metric scores? How do we put them into a ranking? We could, on the one hand, for every participant, aggregate our results, for example, using the mean. Or for every image, we could generate a ranking and aggregate these ranks. Or we could do even more advanced things. We do statistical testing, so pairwise testing of algorithms, and count how often an algorithm is significantly superior to others. All of these things are possible, and there's no right or wrong. So what should I do? We had a look at whether this really makes a difference. So how robust are rankings? So we had a look at data from a conference, and we checked these ranking robustness. So this is an example from a real challenge where we had 13 algorithms and the ranking that is generated when we aggregate using the mean. Then we thought, okay, if we exchange mean by median, shouldn't change that much, because the best algorithm, the winner, shouldn't change. However, if we use median instead of mean, we will see that the ranking actually changes quite a bit, because rank 1 and 5 exchanges their ranks. And if we're honest, if we look at the ranking with 13 algorithms, we don't look at rank 5. So it really makes a difference, a very important difference. And this is just one example out of many. So we found that challenge rankings are extremely sensitive to a range of different parameters. So for example, which metric or variant of a metric do you use? How do you aggregate? Do you use mean or median? And also, who annotated the data made a difference in the rankings. To illustrate this a little bit more, we took another challenge And we calculated 12 different ranking schemes where we exchanged those things for example, which metric variant or whether we use mean or median and so on. And I highlighted 3 algorithms here in different colors so that we can see the differences when we look at the different ranking schemes. And as you see, the rankings change completely. So while algorithm 1, the winner is, for example, quite stable across the first 4 ranking schemes, it suddenly drops down to rank 11 after ranking scheme 4. Then another algorithm from the middle is suddenly one of the top algorithms, and also one of the algorithms that were pretty bad at the beginning is then among the top algorithms. So rankings change completely, and it's completely unstable. So what should you do?
Annika,
Yes.
I have a question.
Sure.
The competitors, are they aware of how the rankings are calculated? Because if you tell them we are going to rank you by the median or by the mean, they're going to tweak the algorithms a bit differently, right?
Yeah. Ideally, they should know. But it depends always a bit on what the organizers put on the website. But thanks to this challenge registration, they should know before, because we have the full design online. So they will probably treat their methods a little bit, to which metric to use, to which aggregation, and so on. So, but good comment, that makes a difference. And that's also one problem of not reporting things or changing how you calculate a ranking. Okay, so what can we do to deal with that, with this ranking uncertainty, with this ranking robustness or insensitivity? One important part is result visualization. So here we have 2 examples. Let it be a challenge or a benchmarking experiment, doesn't matter. We have 5 algorithms each. And for each of these algorithms, we plotted the metric scores in form of box plots and the individual metrics as dots. And we see that for the first ranking, it's very clear. So we directly see here a very clear ranking that algorithm 1 is definitely better than algorithm 2, and this one is better than algorithm 3, and so on. While at the bottom, it's not very clear. If we look at this plot, it's not straightforward to tell which one is better. Perhaps this one is a bit better in terms of the median, but others are better in terms of variability. So really not straightforward. But if we now calculate a ranking from this, we'll see that both of them yield the exact same ranking table. This shouldn't be a big deal, but the problem is that often in publications, we only see the tables. We don't see the plots. So already presenting these box plots is a very important step for us to be able to see if we are really outperforming others or if it's just by chance. And in our work, we also worked on more advanced visualization techniques. For example, we explain in a little bit more detail in the paper if you're interested. If we're doing bootstrapping, we could have a look at ranking uncertainty. So if we're slightly changing our data sets a little bit, we can see how the ranking changes. And this can also be put in a visualization, as you see here. So here you see the algorithms and the ranks plotted against each other among the bootstrap samples. And the radius of these blobs indicate how often a specific rank is achieved. So, for example, in the first case, the rankings are absolutely clear because algorithm 1 is always at rank 1. Algorithm 2 is always at rank 2. While in the bottom case, every algorithm achieves every rank at some point. So this is definitely not a clear ranking, and something where we could, for example, in a competition say, well, we don't have a clear winner, but we have a group of winners, which is also a possibility. If you're interested in this, we have put this into a toolkit, which is open source. You find the link below here. So you basically just put your metric values in a CSV file, and you get a full PDF report out with different kinds of visualizations. So not only the one that I presented, but all box plots, statistical analysis, comparison of different ranking methods, which is also very useful if you do, for example, if you perform your method under different hyperparameters and want to see which performs best, also under ranking uncertainty. As I said before, the metrics are an important part, an important parameter for the rankings. And the metrics also change the rankings. So the next thing that we had to look at are metrics. And this topic is just really close to my heart. So we found that it is really an important thing that we need to consider and often underestimate again. So I'm from healthcare, and if you work in these areas, brain tumor segmentation is the most common task that you will see around, because it's also a very important problem that people need to tackle. So here you see the brain scan of one patient. You see the reference done by a human doctor and the prediction done by an algorithm. And if we look at these two, we see that the tumor is actually segmented very well by the algorithm. We also get a very high metric score of 94%. So indicating that this method has state-of-the-art performance, that it's as good as the doctors. However, in medical imaging, we often have 3D images. So if we look at a different slice of this very same patient, we see that the algorithm is actually systematically missing the tiny lesions. And from a clinical perspective, the tiny lesions are the most important thing to assess in for brain tumor segmentation, because these lesions indicate whether the tumor will progress. So whether we can tell the patient if the tumor is gone or not. So these are very important. But the problem is the metric doesn't recognize this. The metric score is still very high, although we miss the important lesions. And the problem here is the way how we calculate the metric, because the metric basically counts the overlap of pixels between the reference and the prediction. And from a pixel perspective, these few pixels here from this tumor doesn't really matter. They don't concern the metric. So this is one example of where we should use a different metric. For example, number of missed lesions. Quite simple, but definitely here we see that there's something going on. But the problem is, I think, also from a general education perspective, if we're developing an algorithm, at some point we have the situation where we have to decide, okay, which metric do I use to validate my algorithm? So, but there's so many different metrics out there, and how should I know which one is used for what purpose? What are the pros and cons? So that's basically not really possible, because in universities and tutorials, you basically always see the same metrics. And we also had a look at how metrics are currently selected. And here we took advantage from the registration of challenges, because we have one parameter in our guideline, which is justification of metrics choice. So people had to somehow justify why they used a specific metric, and we had a look at these responses. So these are some of the original answers that organizers gave, and many of them said, yeah, well, it's a widely used metric in the field, it's the standard metric for these kind of problems, it's a widely used metric, indicating that we are often using metrics because of their popularity and not ideally because of their clinical suitability. And if we look at some numbers from challenges, we also see that the accuracy is by far the most commonly used metric in classification competitions, indicating that we often use the very same metrics for a specific type of problem. But we should be aware that each metric has limitations, and the accuracy has a very prominent pitfall in the presence of class imbalance. So let's have a look at this example of a binary classification task. Very simple problem in healthcare. You have an image of a patient, for example, a CT scan or an X-ray of your lung, for example, as for COVID. And you want to classify whether the patient is sick or healthy. Let's assume we have this imbalanced data set here, and we have an algorithm, we train on the data set, and we get an accuracy of 97%, which is, of course, a great score. However, our algorithm, in reality, always says that the patients are healthy. Because of the imbalance of the data, it's somehow logical for the algorithm to assume that in most of the cases, people will be healthy. But of course, this also makes this algorithm very useless in practice, because it's not really doing what it's supposed to do. And the problem here just lies in the formula of the accuracy, where it is not related to class imbalance. And there are other metrics, for example, the balanced accuracy, as the name already implies, which are much more suitable for this and also indicate that the algorithm is not working well. And class imbalance is something that is especially relevant to healthcare, because when we're training algorithms, we typically want to make sure that we have a balanced setting. So our algorithm needs to see enough samples to train on to be able to understand what actually makes the disease the disease. However, in reality, if we then deploy our algorithm in the clinics, for example, disease prevalence is typically much lower. It's not 50%, but it's perhaps 2%, 0.5%. So really, really low disease prevalence. And this is exactly why we shouldn't use accuracy in healthcare, or why we should be very careful using that, although it is one of the most common metrics. In other things, the problem is not only because we're choosing a metric with a pitfall, but it's often also how we phrase the problem. So there's often a bit of a mismatch between how we call a task and what was actually meant by a task. And object detection is a good example for that. So in object detection, we're typically concerned about roughly localizing an object in a scene, for example, by using a bounding box, and we want to classify this object. So we're not always interested in pixel level accuracies, but often in practice, I see that the segmentation metric is used to validate these problems. So if we have a look at an example, so this is a polyp detection from colonoscopy. This is the data that I mostly work on. Here we have 3 polyps, and we just draw a bounding box on that in the reference from the doctors. And if we look at 2 potential algorithms, algorithm 1 and 2, and I think, it's getting quite obvious that algorithm 2 is better, because this is detecting all 3 of the polyps, while algorithm 1 is only focusing on the large polyp. However, our segmentation metric will tell us that actually algorithm 1 is better than algorithm 2, which is of course problematic, again, because we're missing the tiny polyps. Similar problem to the brain tumors example. We're always interested in the small things because they grow. But if we have a look at a more like standard computer vision problem, we have this image here, like a scene of bikers, and we want to do a binary segmentation on that. And we're interested in the boundaries, so we want to get the shape correctly of all of these persons and their bikes. If we look at those 4 predictions, I think we would agree that not all of them are good, as some are really random. But the standard segmentation metrics will tell us that all of them are of the same quality, which is of course not the case. So I could go on and on and on, talk about all these pitfalls, but this is not the core of what I want to say. It's just important that every metric has limitations and also, of course, advantages, but we should be aware of that. And this is basically not possible. So we collected many, many pitfalls, but I'm sure they're still missing. So if you want to look at that paper and if you see something that is missing, feel free to contact us. We're always happy to add more to this research. But it's always good to uncover problems, but we also wanted to solve that. And here we founded what we call the Metrics Reloaded initiative. So we got a little bit inspired by Matrix. But this is a multi-center initiative with many, many researchers, more than 70 researchers that work together to find problem-aware metric recommendations. And here we had a bunch of different expertises. We had people from standard machine learning, from working in medicine, from working in biology, really the clinicians, the biologists, statisticians, and so on. So many, many different people from different domains that are basically doing similar things, but we wanted to put all of this together to get a comprehensive picture of what we should be doing. So the important point here is really the problem aware. We want to avoid that we're using metrics because they're popular. We want to come from our research problem. And here I have put biomedical, but it's basically generalizing. So it's basically any kind of image-related research problem. So we come from that problem, and then we're abstracting from the problem. So we collected a bunch of relevant problem properties, which more or less a couple of questions that we asked, which we call this a problem fingerprint, and I will explain this a little bit more in a second. But just so generally, we have a problem, we abstract from the problem, and based on this fingerprint that we then generate and a bunch of potential metric candidates, we can then define what are the metrics that are most suitable for the problem at hand. And the core point here is the problem fingerprint. The problem fingerprint actually was derived from all of our pitfalls that we collected. So we collected all of these problems of metrics, and we wanted to know, okay, what do we need to do in order to not fall into these pitfalls? So one example would be important. Are we interested in boundaries of structures? So if we think of this biker examples that I showed earlier, here we would have said, yes, I really want to have accurate boundaries of my structure. I'm really interested in the contour of objects. In that case, I should have used a different metric. But perhaps we're saying, well, I'm mostly interested in the center of the structure. It's not really important that I have pixel accurate contours. Then we should have used a different metric. Do we have only very small structures in the images, or do we have also large structures? Do we have class imbalance? And all of these things matter when it comes to metric selection. So we ask these questions so that we're somehow get this fingerprint, this list of yes and no's, more or less, for the different problems. And this allows us to generalize across domains. So it's not important anymore what kind of image we have, whether it's CT or microscopy or even something that is more like a photograph or a satellite image. All of this is possible. It's only important that it's a kind of classification problem, because here the validation is quite similar. And with classification, we mean the standard image classification. For example, you have an image and you just state whether you have a tumor or not, or you do that classification at the object level. In that case, it's basically what we saw before. It's object detection. You draw bounding boxes, for example, around your object, and you classify that object. If we do it at pixel level, so for each pixel we do a classification, then would be in the case of semantic segmentation. And if we combine the object and pixel level information, then we have an instance segmentation. So these are the 4 tasks that we currently look at in the metrics reloaded framework. And without going into too much detail, we combine all of these because they're similar in the way how they're validated. So this is the framework, so the core of the framework, which looks quite complicated, and I won't go into detail, so don't worry. But just as you see, the 4 colors of these arrows indicate which of the 4 problem categories we're in. So for example, if we're in image level classification, we just follow the blue path, we ignore everything else. And if we only focus on that, it will directly look much easier. The core concept here is that we have 3 different steps. So we have the first step of generating this fingerprint. So we're going through all of the questions, we answer them, and we save that for later. Then in the metric selection, we're doing the interesting things. We follow the path that we're on, for example, the blue one for classification. And then we have all of these different nodes of different kinds of metrics. So for example, accounting metrics that are based on the confusion matrix, or multi-threshold metrics that are based on these graphs, for example, area under the curve. And for each of these types, we have a bunch of candidates of metrics. And the plus symbol here indicates that there's a decision tree behind that, which guides you through the problem fingerprint and recommends the best suitable metric. Importantly, we not recommend to use only one metric, but we're recommending to use multiple metrics to get a comprehensive picture of what our algorithms are doing, because every metric has limitations, and if we use multiple, we can compensate that. And in the end, we give some recommendations on how to apply these metrics. So for example, how to aggregate them. But we know that the paper is quite complex, so we have very long supplementary and so on. So we wanted to make it a little bit more accessible to users, actually. So we asked the community, what are the use cases for which you would like to see recommendations? And here you see just a few of them, but we asked them for concrete scenarios in the biomedical domain. We generated the fingerprint with the experts, and then you can directly look up the metric recommendations from the framework. And in the last step, we also implemented this as an online toolkit, which is already available, where you don't have to worry about any of these theoretical considerations. So you're just guided through the framework on the fly. So you just need to say, okay, which is the task that I'm currently in? And the framework guides you through all of the questions of the problem fingerprint. So you're getting presented with the question, you get some explanation on that, you give you the answers for your specific problem. And while you're doing that, the framework or the website will then at some point provide you with the metric recommendations. So you don't have to worry about going through all of these graphs. You just see the metric recommendations popping up from time to time. So this is, for example, the first metric. The second one will pop up after you, after you're done with all of these steps. So coming back to what I was talking about in the beginning, when I was talking about challenges as a framework for trustworthy AI. So let's now just assume that challenges start really focusing on clinically relevant metrics or relevant rankings and so on. So just doing a very thorough, comprehensive validation, which is, of high quality. Then AI researchers will hopefully adapt to that better practice because they're typically copying what challenges are doing. And in that case, hopefully at some point, challenges and generally algorithms in healthcare, but also beyond, will reach a higher level of trustworthiness. And with that thought, I would like to thank you for your attention, and I'm happy to take any questions.
Okay. Thank you very much, Annika. That's a very, very nice presentation. It's wonderful. Okay, so maybe I'll ask a couple of questions, use the privilege as a host, and then we open the floor to the participants. So challenges are good, and in fact, we see all the tables that you've shown, right? And the articles, we see them all the time, right? In these machine learning and AI papers. What do you think about replication? Because one thing is also like, so you have like one model that might be the number one, the winner of the challenge, then you can try to replicate, and sometimes you don't find the same results, right? So this would be also useful, or even like to document the poor performance of the replication could be also scientifically useful. Maybe it's difficult to publish, but for the community, it'd be good to know that this is not replicable, for instance, right?
Absolutely. And this is an extremely important part if we talk about AI, because AI is non-deterministic, and we will get different results even if we fix random seed. This was part of my thesis defense, so I had a very long read into that topic. But also something that we are currently looking at future research. So we are currently investigating general variability of studies that can just come across among the data set, but also for the algorithm itself. If I run them again, they will have different results. And if I have a variability of 3% in the scores, can I really claim that I'm better if I'm only 0.3 better than the others?
I think in AI, for instance, like when people move from like, let's say, TensorFlow to PyTorch, or the machines are different, the results can be different too,
exactly.
right?
Exactly.
And in one of your research, so this is probably not this one, but another one, I think I was reading briefly, you are talking about annotators. So like annotators that you use, like mechanical Turks versus experts. Can you share briefly your results of what?
Yes, I haven't had the time to talk about it here. I briefly, roughly mentioned that annotators also have an influence on the rankings, but we had a look at labeling instructions. So This is especially important in healthcare because doctors themselves are not, do have variability on how they annotate something. So if you give them an image and say, segment this tumor, you will get different results. And we found that the labeling instruction, so the instruction that you give to these people, let it be doctors or whatever type of person, they will make a difference. So we had a look at professional annotation companies for this crowdsourcing, for example, Amazon Mechanical Turk. And we found that it really made a difference on how we have these labeling instructions. So our main finding was if you just put text, people won't read it. You can put as much text as you want. It will not really make a difference. Sometimes the results will even get worse. It's always good if you have these annotation instructions to put some pictures. For example, what do you mean by a specific thing that you see in the images? And then they directly know how to actually annotate that. And that's also important as also for challenge participants. So if you're participating in a challenge, you need to know how edge cases are dealt with. So in order to make your algorithms working on that.
In another something related, that's not imaging, but in generative AI, right? You have the large language model. You have this reinforcement learning with human feedbacks, but they also use like equivalent of annotators, right? Like you have humans giving feedbacks and answers of the LMs. It'd be interesting to see also the variation of answers, who their level of education, or geographical region, or are they like native speakers and non-native speakers, and so on, how it affects the performance of these models. So these are very okay, so let me open it to the floor. If there's okay, I see someone.
Yes, thank you for this presentation. Yes, I came in a little after. I was coming from somewhere, sorry. But I heard you say something about a link or something. I don't know if it was in the chat, or is there a way we can, is it some of the information that you were discussing, or?
Yes, I can also share it again in the chat afterwards. We do have a link for a ranking uncertainty analysis toolkit, and we also have a link to the metrics toolkit. So if you're interested, I can just paste it in the chat.
Yes, I would appreciate that. Thank you so much.
Sure. I'm just opening that. We'll post it while I'm waiting for another question.
Any other? Okay. Yes, go ahead.
Hi. This was a very interesting presentation. I thought I learned quite a bit from it. But I would like to learn more. You know, if there is any reading material, you can probably send it to Min, and Min can forward it to people who are interested further.
Yes, absolutely.
But yeah, but I had another question in this, you know, particular towards the end, when you said that, you know, if you run the same algorithm again, you may get a different answer. So is there some way of doing like cost benefit analysis of, you know, being wrong, in the sense that you look at people and you say, oh, you know, it looks like this person, my algorithm tells me this is where the tumor is. But can you really take the risk of, you know, cutting the patient up and chopping that thing and etc. And then you run the algorithm again and you find, oops, it was somewhere else. So is there a way to say that, you know, even when humans are involved, there is a risk that there could be a mistake? Okay, so nothing is risk free in that sense. But is there a way to quantify the level of accuracy or the level of confidence one has in the finding? That's what. And if there is it may not be possible to answer it here, but if there is a way to people like us can read up and understand that, that will be helpful.
So I don't have something. I'm not sure if that's already solved. I think that's up to research. I just remember from one paper that had a look at if you run that algorithm again, how large is the variability. And I think they somehow stated something like you need roughly 16 runs to somehow quantify the variability. So I think running again is an important part. There are also things that you could do for like strength weakness analysis of algorithms. This is something that we also proposed in the past. It's a bit of a different direction. It's more like, okay, what are the things that my algorithm currently cannot handle? And we did this with a statistical mixed model analysis, but I can also share that publication. But generally, I think there's not a concrete answer to that. But I think that's exactly the things why it's important to have a look into all of these validation related things. So we want to make sure if we're using AI, especially in healthcare, that the algorithms are not doing strange things.
Yeah, thank you.
The questions for Annika? Maybe I'll ask one question. So I don't imagine that you'll have more and more like what they call like foundation models, like pre-trained models that open source or not open source that scientists can just use off the shelf and then fine-tune on their the specific task. So in that case, there's a huge variation in terms of training data, right? Some models are very big, some are smaller, and so what are your recommendations when when competitors are using pre-trained models?
Yeah, it's a good point, and something where we just went into it because these foundation models are very new, and we now need to see how we validate it. There are just multiple things that we need to consider. Are we having a validation strategy on all of these different data sets, or do we only focus on the downstream tasks? So it's not solved. So I cannot give you a complete answer here, but we're working on that currently because it's such an important topic. And I have the feeling that the AI community, especially in imaging, is really shifting towards foundation models. And yeah, we need to consider that, but I don't have an answer so far. Yeah. Hopefully in a few years.
There's a saying, that when something becomes a matrix or an objective, like we do it more in economics, that it stops to be useful. So for example, they do it in monetary policy when you use like interest rate as a target. Then it stops to be useful because all the participants are looking at that objective, optimized towards that objective, and then so it doesn't. Yeah. So do you have observed some? Do you have you observed something similar in these medical challenges when you focus on one particular matrix, everybody optimized towards that matrix, but it makes the whole model or the whole framework like not as good?
Yeah. All the time, because people tend to just do the same metrics all over the place again. And whenever I see that metric, my head is already skeptical if it's correct. Yeah, I think that we always have these trends. And also, I don't remember which metric it was in particular, but we also had the case that I don't remember if it was a challenge or just an important benchmark, whatever. They used a metric in a paper, but they did it wrong. And then everyone else did it the same wrong way for a couple of years.
Oh, wow. Yeah. That's bad. Okay. Any other question? I had yeah, so there's that matrix things. And in terms of, so this, I think your talk is very interesting. It's very important it shows that you have the importance of domain expertise, right? You cannot just take like off-the-shelf stuff from like, from the computer vision community and just transfer to your domain, right? You have to work with like, domain experts, doctors in your case, or physicists or radiologists and so on to get the right metrics. I think that the examples of the size of the tumor is not only like per voxel that you have to optimize, but it has to be also, do you get the small and the big tumors, and maybe the small tumors are more important than the big tumors, as you mentioned, and we see that. But how how do you collaborate with the domain experts who are not AI or machine learning experts or statistical experts? How do you bring build a bridge with that with these domain experts? Like could be like doctors, but who never did like computer science or mathematics.
Yeah, it's not always easy. Especially sometimes we use the same terms for something completely different. And one of the first things that we did in the metrics initiative was defining terminology across all of these different stakeholders. So typically, let's say clinicians that are working together with AI researchers, they somehow have a rough understanding of what's going on and they're interested in learning something. But there are definitely people that are not interested, where it gets complicated, and you have to spend a lot of time from both points of view to explain what you want in easy language, and that's a challenge.
Yeah, that's true. Yeah, I think I was reading that even like the statistics, like the doctors, the statisticians use different metrics and so on. So some of them are very understand like specificity, sensitivities of other community. They use recall, precision, and recall.
Yeah, exactly.
They don't know exactly what's the difference. Any other questions? You have a top experts in this field, but I recommend you. So you have a web page, have a Google Scholar page with all your publications, and feel free to contact Dr. Reinke if you have any further questions. But so thank you very much for that excellent presentation. So I'll put out a recording. So I think it'd be very useful. But I think it was like AI in healthcare, but I think all these ideas are like applicable like beyond healthcare, right? Like in many other fields. I mean, the question of metrics challenges, it is something that you find in many other domains. So thank you very much, and thank you very much to all the participants. And next time our special guest will be AI. So we'll be also like on AI risk. Will be an expert who comes from banking. He'll talk about AI model risk management. Right? So also like how AI can go wrong, but from another perspective. Okay, so thank you very much, and Annika, have a very nice evening in Germany. Okay.
Thank you.
Goodbye all.
Bye bye.